Yeah, this equation. So
Is it here?
yeah, this equation 9.
Yeah.
So it says instantaneous irradiance is computed by fitting this curve up to daily total irradiance. So when the, let's say I'm running the model at time right now, like 11:02, the LG sees the current date total irradiance, then converted to this, or yesterday's.
Oh, let me hear again, please, the question.
You would, if I can, you specify the daily irradiance
Right, for today.
for today.
Yeah.
And then and basically what it's doing is taking that total irradiance and apportioning it how it would occur during the day.
Right, so actually at this moment, it's somewhat like the LG is sensing like what's happening in the whole day.
Well, no, for that time step, it's taking whatever the daily average would be,
Right.
and it would be somewhere up here in that curve, and that's what it would see for that time step. And if you went 5 minutes later, it would see that, and if you went after lunchtime, it would start coming down.
Right, but you already calculated the daily total.
No, you didn't calculate, that's an observation. You specify.
Right, you already
Okay.
observed it, but what I mean is when you simulate to this current time, LG does not know what's happening.
Yes, it does, because it sees the radiance comes down from the sky and hits the water and goes through the water column. So all it knows is
But
it's
that
exposed
is
to
based
that.
on the daily total observation.
Well,
But
that's,
daily total observation, you only know that after the day has passed.
well, but think about Carl simulating 1984. That's, 40 years ago. You're not really
Right,
trying to simulate this
we
very
know,
minute.
we know what is the total irradiance on any specific day.
Yes.
But what I mean is when you simulate that, at this current time step,
Yes.
11:03, how LG knows.
Because the sun is changing over the day, the irradiance is changing over the day, and that's what's hitting the water surface, and that's what the algae are exposed to.
That's like, for instance, we only know the total daily irradiance for today by tomorrow. Right?
No, but think about it, again, Carl's doing a simulation that starts in
He's not
1985. He
doing a
knows what
prediction.
the irradiance was in 1985.
He's not doing a prediction, this is a historical simulation.
Right.
So he's simulating what would have happened
Right,
in
I understand. I was
1984.
just trying to see like,
If you were trying to use it in prediction mode, this is something that I do. then
so
you
my
would have to
next
predict
question is
the
actually, why don't we just use observed instantaneously?
Because nobody measures it from second to second.
No,
Or that type of
hourly,
hour.
Hourly, yeah.
Well, but
Hourly,
because
then
most of the time what's
interpolation.
reported to you is the daily.
Okay. So back then, it's daily. Now we have actually hourly.
You could perhaps
Hourly
change
or
it.
15 minutes.
Right.
No, actually, I think that would be, I think we're on the same page here. The distribution of the irradiance over the day will make a difference because the response is nonlinear. So the more relatively higher instances of irradiance relative to lower cloudiness, periods of cloudiness during a day with the same total irradiance or variations in a day with the same total irradiance should, on an instantaneous basis, reduce the productivity. The variation will produce the variation, depending on how it goes, will likely reduce the productivity, and you don't capture that here. You don't capture that because you only have the daily stuff, and you got to do something with the daily
Right.
stuff.
And actually, another way of looking at it is that, you are getting daily irradiance from, for example, Washington DC, National Airport. How does that apply to Chesapeake Bay? These are cloud differences.
right,
So you're right, but that correction that you're talking about might be more of a second or even a third order impact.
Yeah.
So I remember somewhere, I forgot the paper's name, but they were mentioning, the LG's response to irradiance is also related to what they sense earlier, like the day before or the day after. So I was thinking maybe it's related to somewhat, that's why using the daily total irradiance, then back calculating the instantaneous. But in this case, it's probably not the case.
Right.
Okay, well, that said, where's my, okay, so we're going to move on to the next time. Yeah, go ahead.
Before you do,
Bob, go ahead.
so when you calculate salinity, you just take the initial conditions from your hydrodynamic run and then use that to start the ICM run?
No, if we want the initial salinity, we do like a spin. Well, it depends. All right. If we're just interested in predicting salinity, we get our initial conditions by spinning up. All right. What I mean is we have some sense of how long it takes the bay to come to equilibrium with the forcing functions, and we spin the model up. Now, if we were doing what you're saying, or if we were trying to validate our linkage, then we would want to take the exact same initial conditions as the hydrodynamic model uses. But for a typical run, the initial conditions are obtained by spin up. Okay? Did I hear an okay, we're going to move on, right?
It was just different than what I had thought. I was with him. And you would have an initial salinity conditions back.
Okay, lecture 3, lecture 4. You know, it's the devil. If you think about it, so there's 59,000 cells in the Bay model, and to specify initial conditions in 59,000 cells is the devil. And, you know, and to specify, well, it's the devil. You know, I guess you could put it out from the hydro model, but we also need initial conditions for the nitrogen and the phosphorus and the oxygen and all these other things. And, you know, conventionally the way we get those is by spinning the model up.
Oh, spinning is a good question. When you do a scenario run where you reduce the nutrients, do you cycle the model? Maybe one, so you do, you know, okay. And the reason I'm asking that is it's going to take a while for the sediment model to respond to the load reduction, so you do spin it.
That's the first exercise after lunch.
Ah, okay.
Okay, so you should have, in all that material you downloaded, you should have a chapter entitled Light Attenuation. This chapter comes from the, this chapter comes, I'm going to blow that up a little bit. And we'll go a little bit this way. Well, anyway. This chapter comes from the most recent documentation, so it's up to date. And this has changed considerably from the previous version of the Bay model, so you're going to want to keep yourself, you know, up to date on this. Or the previous documentation is woefully obsolete. Okay. For light attenuation, we use what's called a partial attenuation model. And basically what it says is that light attenuation is some background value plus some fraction or some function of suspended solids plus some function of something we call color. Okay, easy enough. An optical scientist, a real thorough optical scientist, will look at this relationship and spit. As with some of the things we did with relating irradiance to Langleys or Watts, you know, this is actually a very good approximation. So for our model, this is what we're going to do. A couple of issues are, one of the issues are, you know, a function of suspended solids, but we have all different kinds of solids, right? We have fixed solids, which are sort of, you know, mineral, dirt, volatile solids, which are organic matter, chlorophyll itself, independent of the algal biomass. Chlorophyll attenuates light, you know, that's where the energy comes from. Okay, so there are all different kinds of solids. Now, color, we really don't have any measures of color. What you can do are use analogs for color. A popular one is DOC. It turns out that's a crappy analog for color, except in very rare systems. And I'm not sure why that is. but it may be because the DOC is an inaccurate measurement. I don't know, but you know, if you use regression and try to relate light attenuation to DOC, I'll be very surprised if you get anything. Oddly enough, it turns out that salinity is a very good in Chesapeake Bay. Salinity is a very good indicator of color. And what it says is, and we'll see this in a few minutes, fresh water tends to be colored. Okay, there tends to be colored, you know, yellow. There tends to be colored material in fresh water. On the other hand, really nice ocean water is not colored, right? It's clear. So it turns out, and we'll just empirically, it turns out that a salinity is a good indicator of color. We'll let that be.
So, Carl,
Yeah.
when you mentioned color, do you mention CEDA? Are you saying CEDA?
Yeah.
Yes.
Yeah. Okay. So what we did, we proposed a model. We have tens of thousands of measurements of light attenuation in Chesapeake Bay, and those, depending, but those measurements are accompanied by usually by a very good water quality data set. So as I mentioned to you, there are all different kinds of solids out there, different kinds of solids measurements. So we used basically a stepwise regression. And what we found was, for all intents and purposes, total suspended solids was as good a measure as any. You know, we tried, for example, to isolate, let's say, fixed solids from organic solids. You know, fixed solids, it means inorganic. And we tried to see, did we get a better relationship if we used inorganic solids and organic solids, and then potentially allow them to have different attenuation coefficients? And practically speaking, total suspended solids was as good as anything. Let's see, what have we got here now?
I'm sorry, so total suspended solids is the sum of the organic nitrogen, blah, 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 and the phytoplankton?
Yeah.
Okay.
I mean, actually, this is for the moment, this is a laboratory measure. You know, we're going to get the water, we're going to filter it, we're going to dry what we filter, and that's total suspended solids.
Okay.
And we find, what we have to do, and we'll go over that in a couple of slides. So this right now is strictly based on observation, no modeling yet. What we have to do is we have to take the model state variables and combine them in some fashion such that we get total suspended solids. So here you go.
And I'm sorry, one more.
No, go ahead.
You mentioned the measures of attenuation. How much of that was Secchi depth, disk depth versus profiles of attenuation?
Lately, the Bay program just uses LICOR exclusively. So everything that went into this is a measure of attenuation. Yeah,
okay.
we don't use Secchi depth at all
Anymore. Okay, thank you.
Let's see, next one. Okay, so there are the parameter values. The background is look at that, four significant figures, but the background value for attenuation is about 1.65 per meter. So that's just sort of average. A2, the suspended solids, about 0.5, 0.6 meters squared per gram, and A3 is minus 0.06. The negative value, as I explained, means that fresh water is more highly colored than seawater. Okay, so going back to here, the attenuation is inversely proportional, or the greater the salt water is, this is a negative coefficient. So the higher the salinity, the lower the attenuation, because the water is not as highly colored, is what we're saying. I owe that insight to Raleigh Hood, and I think one of his students. They published a paper on light attenuation in Chesapeake Bay, and that was, never would have occurred to me to use salt, but they did, and they had good results, and I use it, and I have good results. Okay. What you can do, and the reason I like this partial attenuation model, so that equation, those coefficients are fit to thousands of observations throughout the Chesapeake Bay system. The tributaries, it's in the Chesapeake Bay database, and you have the accompanying independent variables. We used it. But so then you can examine residuals, and you can say, well, you know, where do we get deviations from this average behavior for thousands of observations? And so you see, for example, negative residuals. The attenuation was less than modeled in a couple of places near the fall lines. Negative residuals in the lower Potomac and St. Mary's River. Positive residuals in the York and Mattaponi. It was interesting, when you looked at this thing, you could pick out places in the bay that were adjacent to wetlands, because the places that were adjacent to wetlands had higher attenuation than you would have predicted based on the complete data set. Why? Because wetlands are a source of dissolved organic, colored dissolved organic matter. So I thought that was interesting, and as I said, okay, so particularly if you're familiar with the York and Mattaponi, you know there's a lot of wetlands there. And for whatever reasons, I can't totally explain, you also got positive residuals in the James and Elizabeth. So what we can do, I don't know if this slide shows it or not.
Lots of crap.
Did I go the wrong way? Okay, apparently not. Okay, but what we can do with this partial attenuation model is we can actually change that background attenuation to account for these residuals. So where the background attenuation is about 1.65 on average, I can make it a little lower, let's say downstream of the Susquehanna. I can make it a little higher in the York River. I like that. Prior to this, we had the last version of the Bay model had an advanced optical model. We've got a top-notch optical scientist to do us a top-notch model of light attenuation that involved scattering and attenuation, and it was good. It consumed an enormous amount of computer time, and it was exceptionally difficult to parameterize because you needed measurements of optical properties consistent with the advanced optical model. And for me also, it was abstruse. You could look at this equation, and if you said, I want to adjust the attenuation a little bit, make it a little higher, oh my God, how do I do that? You couldn't look at it and make use of it. So we fell back to this partial attenuation model, and it's interesting, in the report, I do a comparison of the computed attenuation from the optical model versus computed attenuation from this model, and in almost every system, this model was better. And I think that's largely because we diddle it a little bit. If you really want to know, computing attenuation, the key is, can you compute those total suspended solids? And it's less dependent on the kind of optical model you use and more dependent on how well you compute total suspended solids. So it almost doesn't matter what optical model you use, and you may as well use a simple one.